Desde la Decanatura de la Facultad de Minas, el Centro de Pensamiento, Territorios de Vida, damos las gracias por acompañarnos en este importante espacio donde vamos a tener la presentación del profesor Stefano Uitili de la Universidad de Newcastle, quien nos va a socializar el proyecto con el que la Facultad de Minas de la Universidad Nacional de Colombia está participando en alianza con la Universidad de Newcastle y otras universidades, y con el que nos ganamos un Marie Curie para hacer investigación acerca de hacer minería con sostenibilidad. Quiero agradecer al profesor Stefano por estar aquí con nosotros, por hacer esta presentación, que es muy importante para nuestra facultad. Nos sentimos muy orgullosos de participar en este importante proyecto. Él está visitando esta semana Colombia, así que de manera muy rápida logramos sacar este espacio para poder hacer esta socialización. Sé que hubo poco tiempo para hacer la invitación con bastante anticipación, por eso sé que hoy nos acompañan algunos de ustedes, pero quiero hacer la claridad importante de que se va a grabar esta presentación, la vamos a tener en nuestro canal oficial de YouTube para que puedan entonces acceder a ella con calma, escucharla, y cualquier pregunta pues van a quedar nuestros contactos para que podamos hacer retroalimentación. Quiero invitar ahora a Juan Pablo Izaza Vargas para que presente, como es debido al profesor Stefano. Su presentación será en inglés, y bueno, cualquier pregunta, cualquier inquietud, comentario, estamos muy atentos para poder responderlo. Gracias.
Thank you, Professor Eva, and welcome to all our participants today for this important space, and having had the pleasure to entertain and welcome Professor Stefano this morning. I will now present him as full professor of the Newcastle University. And Professor Stefano did his undergraduate education at the Politecnico di Milano as a mechanical engineer. And then he did his master's in the University of Chalmers in Sweden, and then advancing to the doctoral program at the Politecnico di Milano in also computer engineering. CE, General Engineer, thank you. He also has posted as a parliamentary academic fellow for a project called Does the UK Need EU Funding to Remain a World Leader in Scientific Research and Innovation? An analysis of the impact that the EU had compared to the UK funding, United Kingdom funding on research and development. His first degree was in structural engineering, followed by a doctorate in geotechnical engineering. So he has been with the University of Newcastle for the past 9 years, and he first was lecturer at the University of Oxford. He has also been a representative at the CEN committee, and has been editorial board of several spaces and research spaces such as Geotechnique, a member of the Engineering and Geology, the board member of Rock Mechanics and Rock Engineer, a fellow of the Geological Society of London, and a member of the International Technical Committee of some other European organizations. So right now, the presentation is basically going to address, like the Dean just said, initiatives that mostly involve the present state of open mining. And obviously, the European Union has been interested in how the development of these spaces, especially in Central and in Eastern Europe, in countries such as Serbia, have been handling the open pit. So for Universidad Nacional, it's been an honor to participate in the consortium, and now we have begun the execution of the program, which will last for the next 4 years. So with that, I leave you, Professor Stefano, and thank you for your visit.
Thank you very much, Juan Pablo and Eva, for such a wonderful introduction. And when the introduction is too good, I'm always a bit scared because you don't want to then be disappointed. So hopefully, my hope for today is to keep up to such a wonderful introduction. Just a question about the mic. It's okay, so I'm supposed to speak with this, yeah? And my only other question is if I want to, she does, so I say next, okay, thank you very much. So basically, this is, what I want to do, guys, is just to introduce you, first of all, to the idea of what does it mean topological optimization, just with this simple slide. So here, I will talk about my research, which is about finding, working out better ways to design slopes. So on the top, you may see a slope or an ice cream cone. We all are familiar with ice cream, right? And instead, on the bottom would be this optimal slope. And then I'm going to talk about this. Next, please. But first of all, before the attention may drop, I want to tell you a bit more about this EU program that has been mentioned. So this is a Marie Curie staff exchange, it's called. And basically, as you can see, there are 12 partners, and Universidad Nacional de Colombia is one of them. And maybe if we can go to the next slide now. Sorry, next, please. Next. Yeah, there is a bit of animation. Okay, next. Okay, perfect. So the project summary. So we may spend well, let's say a few 1 minute. So okay, the context is European Union is now very keen to decarbonize mining, but especially to make mining more efficient, because there is a specific law, the Critical Raw Material Act, which is a very important policy document that the European Union has done in order to then be able to put resources into mining. So it's not just talk, it's also money, because there will also be so-called pillar project, where basically, for instance, next year there will be one call, and then there will be various calls purely focused on mining. And the idea is that is recognized mining is very important for the energy transition, because we need the lithium, the copper for electrification, lithium for e-battery, stuff like that. Okay, so this was literally the sort of brief introduction to the proposal, which actually the reviewers quite liked. And then, in terms of the topic, the proposal is around how we can make mining more efficient, and in particular, with topological optimization, which is one sort of specific topic, but also automating pit design. So the idea is, if we can use the software and making more digital the designing mines, basically. Okay, I think this is the main point. Next slide, please. Okay, perfect. So this is about to see how it works in terms of this grant, because in a way, also, I think a key reason why I'm here is because I would like to, when I take my flight back, basically, to the UK, to have in mind people who, from Universidad Nacional, can take part in this program. So obviously, the first question for you is, okay, what do you need for me? And the idea is that you can go to one of these 4 universities. Newcastle is the coordinator, and then there are Universidad de Vigo, Universidad Politécnica de Catalunya, which are 2 Spanish universities with quite a strong mining and geotechnical tradition. And then the Mining and Metallurgy Institute in Bor. Bor is really the capital of mining for the Balkans. So it's an institute, it's a research institute, not a university, but a research institute which specializes in mining. Am I going too fast, by the way? Please let me know. Okay. So basically, for the people who take part, it works like this. Okay. Academic staff, so anyone who is a staff, professor, associate professor, assistant professor, postdoc, any type of staff, as long as you have a contract, I guess, with your Universidad Nacional, and PhD student. So all these people can take part, and the idea is a sort of per diem forfeit reimbursement. So you will receive 2,710 euro per month, where a month is 30 days, and then you can do the sums. So if you have a secondment of 4.5 months, it will be 12,195 euros. So it's very simple, not the calculation. It's all proportional to how long you stay in one of those 4 institutions. The ban is meant to pay for travel, accommodation, and if you make any extra money, so if you spend less in travel and accommodation, it's all good for you because you keep the money. So I think in terms of points, another point is the money will be paid to the visiting researcher by the host institution, because this is a feature of this European project where the money physically stays in Europe. This is what the European Union wants. So the way it works is like the person will be paid, the researcher, but directly by the host institution. And then, of course, there will be events like doctoral school, and I would say I'm quite keen on doing events where we piggyback to important conferences. So, I don't want to bore you now with the detail, but basically it's just about this staff exchange. There will also be some specific events, but I think the important thing now is to think in terms of these secondments, no? Because the idea is that to find a topic where you can work at one of these partner institutions, and this, so if you're doing a PhD, clearly compatible with your PhD program. If you are staff, well, you may want to come and discuss with me and say, oh, look, I'm interested in X and that. So it's I think, I really would like to use the time I'm here to discuss potential, projects with as many people as possible. By the way, on the right, those are the scientists in charge. So I'm in charge at Newcastle, but then see those Professor Leandro Alejano in Universidad de Vigo, Professor Enrique Bonet in UPS, and Professor Anna Kozov is instead in charge at the Institute of Mining in Bor. Okay, so these are the work packages to give you just an idea of and I think the title is more than enough, of the content, right? So work package 1 is about topological optimal slope design for pitfalls and tailing. I'm gonna now talk for the next 10 minutes about it, so you will know exactly what it is, trust me. Machine learning for slope topological optimization. In reality, actually, I would say machine learning for mining, no? So clearly, personally, I would prefer to, if somebody works in machine learning, to try to find a topic within the area of this slope optimization, but I think machine learning is a wonderful cross-disciplinary team. So if you work in machine learning, I think it would be super easy to find common ground. Advanced numerical modeling for rock discontinuities and anisotropy. So for those of you who work in rock mechanics, I think there is exciting stuff, because this is still a frontier, how we characterize jointed rock mass discontinuities and the effect of discontinuities on the behavior of the rock mass. Case study to quantify optimal design. I'm just talking about optimal design in general, no? So optimal design benefit via life cycle assessment. So the idea is to use some quantitative methods to work out the benefit that a more efficient design provides to the mine. So to me, this means, in terms of benefit, If we are more efficient, should be higher net present value, right? Increase the profitability. But environmentally would also be carbon emission. So to have a methodology where we calculate the carbon emission, CO2, that comes from drilling, blasting, comminution, all the excavation, all the processes that are typical in a mine, and also life cycle assessment. Well, it could mean many things to many people, but it's all in scope of life cycle assessment. I'm quite keen on this experimental excavation and monitoring of optimal slope profile, because this is really a big innovation. Basically, if we can find one or more mine here in Colombia where they are happy to try some of the outcome of the grant, I think that will be a very good thing in terms of impact. No? So the work package 5 is really about the impact, to say, okay, as academics we tend to do lots of study, but a lot of time the studies stop there. Instead, the idea is we want to implement the outcome in the ideally local mining context, so that we are able to prove a concrete benefit. Okay. So if you have any question, please ask, okay? So any question about the work packages so far? No, okay? So here, and I'm going to talk about this optimization of slopes, why it's important. So, perfect. So basically, just to say that here I'm going to talk about the overall slope angle of a slope. And what I'm going to present you is how we can achieve a steeper pit walls without compromising safety. And we need to abandon the assumption of planar profiles. Okay, so here, let me talk you again. So basically, what you can see here is an open pit mine, right? And on top is, this actually is a real mine, and is a work I've done with the ATCM Center in Chile, in Santiago de Chile. What you see is then the cross-section, right? So you have that ice cream cone, that shell, no? That is a 3D representation of the pit, okay? And then on the right, you see the cross-section in 2D, okay? And the same thing underneath, but it's just a different shape. So the pit has a different shape. And therefore, also on the right, the slope has a different shape, no? It could be, it looks very simple, but now I want you notice one thing. The slope on the right is 34.6 of inclination, 34.6. And the factor of safety, calculated by a professional software called Rock Science Slide, is 1.191. The slope underneath has exactly the same safety, exactly the same factor of safety, but is 4 degrees more inclined, because it's a 38.6 rather than 34.6. So in a way, this hopefully simple slide should illustrate the very point of trying to design optimal slope, because here, purely changing the shape of the slope for the same safety, without compromising safety, we have that one shape allows me to be 4 degrees steeper. 4 degrees, for people who are into the open pit mine sector, know that it's huge. Typically, it depends on the depth, but 1 degree could be anything between 10 and 100 million saved, because the idea is you want to excavate your commodity, the metal, whatever, and now you have a lot of waste rock that is a waste because you need the slope. So excavate at a certain angle for the stability of the slope. If you could, ideally, in an ideal world, you would excavate vertical. But if you go vertical, the slope fails. So you need to have a certain angle, right? But whatever you can do in terms of steepening up the slope means that you avoid pure waste rock, okay? Yes? Yes, yes, no, absolutely. Perhaps the only point I need to say, that was the overall slope. I mean, there was no, but yes, yes. So because I'm used to the click myself. Okay, next. Let's do, no, next. No, previous, next. Next again, okay. So here just to say that is a bit of historical background, okay? So the rock slope engineering is a famous book from Huckebray, which is really, to me, rock slope engineering is like the main textbook. And basically this is just to say that these guys understood that actually there is no particular reason for a slope to be a straight line. And maybe there are some shapes which are better. Also, that is my PhD, a few other articles from other people. So this is just to show that there are other researchers that independently have said, oh, look, if you do a shape which is a circle or some other shape, a log spiral, whatever, actually we can see that, for instance, the factor of safety increases, or basically what I'm showing here, because there is no time to go into detail, but it's like to say that a lot of other people came to the conclusion that a slope, in our mind, is always a straight line because, you know, a cutting, no? But it's not optimal. It doesn't, the fact that is a straight is because our cultural baggage. Also, clearly, if you have just a granular material, so in the morning, if you pour coffee, you know, then of course that will go along a straight line because that is a granular material. But when we are in mining, there is always some cohesion, no? Because a rock has always some cohesion. So for a cohesive material, for rock, the straight line is not at all the best shape. It's just one shape. Next, please. So here is then where I've been working for a few years, I would say, many years, depending on what is few and what is many. But the idea is to come up with a software, which we call it slope optimizer, where what I want is that the software itself gives me the shape of the as a result. Because typically, in all the existing geotechnical software, the slope is given. So you see a geometry and you say, how safe is this slope? And the software does a calculation and tells you a factor of safety or a probability of failure. But we always take the slope which is given to us as if was the best slope, but that's not the case. So the idea here is to have out of a mathematical optimization. Can we go back one? Back, please. No, back. Okay. So the input is stratigraphy, rock properties, bench. So the bench is an input. Ramp, if there is any ramp. Target factor of safety. How safe I want the slope. And then the software provides the shape. Here what I'm showing is that the bench height provides natural discretization. So actually is a 1D problem because typically in a mine, all the benches are the same height. So what I need to work out as unknowns is the position of each of those points, the horizontal coordinates. I don't know the position of any, so you could have 20 variables, 30, 40, depending on the height of the set of unknown variables. Next, please. So find these variables so that I maximize something that is the inclination of this slope. And there are some constraints because we know that, for instance, because we have a certain bench face angle, a certain minimum bandwidth, so the bench is actually exerts something constrained. So it's not unconstrained optimization, which would be easier. It's a constraint optimization, mathematically. Next, please. So this, in a nutshell, now I don't want to bore you, but how does the algorithm work is for every, so imagine you could say, okay, well, the shape, there could be thousands. For every single slope, for every single geometry, we can work out a factor of safety, business as usual, but then in this mathematical optimization, we are trying to find the optimal. The optimal slope is the one that is associated to the height. Next, please. Okay, so and then this is just to say how you work out, because the idea is for a given overall slope inclination, work out the slope associated to the maximum factor of safety, and then want to have an angle which is as steep as possible for a given target factor of safety. So there is basically a loop where you start with an overall slope angle, and for each value of the overall slope angle, consider you find what is the best slope, and you stop the loop when the optimal slope as a factor of safety, which is equal to the target. Here is a bit technical, but it's just to say that basically to find this optimal slope, there are three nested optimizations, one inside the other optimization. Next, please. Okay, this is just a graphical representation where you see all this profile, and then now you can see the benches. So in blue would be the optional slope, in red the optimal slope, and in green is the amount of waste rock that you don't excavate, the amount of stuff that stays there. So it's a visualization of the saving. Next, please. This is just in 3D. So how can you demonstrate the improvement? Planar design from optimal slope. So basically, everything is the same. So we need to be consistent. The input is the same. The only thing that is different between these two designs is the slope. And then the design of the mine is carried out, and then those green volume represent the difference in volume in terms of the rock excavated between the two designs. So if I can estimate that volume, and then I can also estimate the amount of CO2 of emission associated to the volume of rock that I do not excavate. If this hopefully makes sense, let me know. So that is a 3D visualization of the, let's say, waste rock saving, the waste rock saving. Next, please. Yes, this is the pointer, yes. Okay, so this, basically, these are all open access, because when I can, I like to publish open access. So this, in all this open access, basically one mine case study, no? Each. And then in each of them, there is an estimate of the amount of waste rock that is saved, and then also in terms of NPV. Next, please. Okay, so this, I want just to in detail, one case study in detail. So this is a mine from Kinross, and also I worked with a data mine, which is a software company for mining. So the idea is that is a block model, no? So we're familiar, basically the block model is a model of blocks, where each block is a brick. So each block will have a certain amount of concentration, no? So each block, you will say if it is gold, or if it is, here I think it was gold. So you will have, the block model basically contains all the mineralogical data, and then you say, okay, here there are 5 sectors, this is a crest where you're gonna excavate, and for each sector, we want to work out the optimal slope. We know that in terms of factor of safety, there is a target of 1.2. Next, please. Back one. Okay, so here is just to say, again, one simple point. Here is the slope as it was originally, okay? Here you don't see the benches, but actually here you can see the benches. So this is a bench, no? Bench. So the bench face angle will be around 70 degrees. This bench width is the same. It's the same everywhere, no? So this blue line represents the real slope, including benches, and then instead this straight line is a simplification that you do when you do sometimes slope stability analysis, no? And instead, the red one is a result of slope topological optimization. So in the red, we have then this sort of shape like this. So this would be the optimal shape, and this shape allows to be, this is the rose of angle, 34.1 rather than 32.7, no? So there is an extra inclination of 1.5 degree. The factor of safety, and this has been calculated via third-party software, is the same, around the same, 1.2. Okay, and here instead is another sector where, again, linear slope, traditional slope, 34.6 inclination, and this instead is the optimal slope, 38.6. Why now I am showing you these two different sectors? Because what I'm showing you is the fact that actually the shape of the optimal is very different in sector 2 from sector 3. So in sector, no, in sector 2 I have like concave, convex, concave, convex. Here instead it's just concave, convex. And can I show you, like, if I show you other case study, the shape will always be different. Why this is important? Because this tells us that actually the optimal shape is a function of the physical parameter of the rock, is a function of the stratigraphy. So how large is one layer the other. So in other words, will be different for every mine. So you cannot extrapolate from one mine to the next mine. You cannot even extrapolate within the same mine. These are two different sectors in the same mine. So really, unless you use a software or unless basically you redo the calculation, you cannot infer, because the optimal shape is a function of the specific stratigraphy, of the specific rock properties, basically. Perfect. Next, I'm gonna try to now speed up a little bit. Let's skip this. Next. No, next. Okay, you got? Okay, this is just to say, okay, so for each sector, we can calculate, here you can see the difference in terms of overall slope angle. Next, please. And then we did this calculation up to the money, because money talks. Money talks. This is, in England, people like this sentence. So here you can see the difference between planar pit wall, optimal pit wall, and the effect of this innovation. So basically you have essentially much less waste rock. In this case, the optimal pit wall even allowed to get more tons of ore body. Then we can discuss about that, but basically you can get more ore body. So therefore the stripping ratio, key parameter, the stripping ratio is much better in case of optimal pit wall. Then same capex, we work out the NPV, and there is a difference of 13 million, so extra 50, more than 50% better NPV. So I think here the numbers speak by themselves in terms of the improvement, no? Next, please. Okay, this is another mine, just to say that, yeah, this would be just another example. But I think in the interest of time, next, we can skip this. Okay, maybe just to tell you this, you see, and I can also do, once you know what is the amount of waste rock saved, we can also work out energy-wise and carbon footprint. Because all you do, there are equations, there are models where you can estimate for every ton of rock in that specific mine, what is the fuel of the truck, what is the amount of ANFO. So on the basis of the specific number for the specific mine, we work out the amount of energy that is being saved by adopting optimal pit wall, and also the amount of carbon footprint. Clearly, in order to do this, you need to have the data. So you need to, it's all in the paper, by the way, but my point is, it's a quantitative model because there are specific equations to quantify the energy and carbon footprint for the various main activities, so blasting, drilling, haulage, processing, and dumping the waste rock in the dump. And at the end of this, we can work out the environmental benefit. Okay, here is just a summary of the case study. So you see now, talking about environmental benefit, on average, we're talking about 600,000 tons per mine. So not annually, but for the whole mine, but I think this is a big number. This would be the average of the CO2 emission reduction by leaving the waste rock, by having basically a more efficient slope, so that for the same safety, we save on the waste rock. And then also in terms of profit, because obviously the extra profit, it's always in the tens of millions, basically. Any questions so far? Next, please. Okay, here I would skip. I mean, if anyone is interested, basically, this is a software, because basically this is it's a spin-out company now where we also commercialize the software. So basically, we're happy to give academic license for free, but a commercial software that, you know, we are planning to sell to the mining company, but we're also happy to give academic licenses. Next. So I guess in another context I would do a demo, but okay. So this is just to show you the graphical user interface. The idea is that you have the stratigraphy as input, no? You can see different color depending on different rock type. You give the property of the rock. This represents the phreatic line, the water table. Next, please. Here is where you say, okay, the other thing you need to say is where is the crest of the slope. You specify a depth, no, an excavation depth. Next, please. And you get your optimal slope as a result. And then you can take this into, well, if anybody is interested in strategic mine planning, we can have a discussion, but this is just to say that the software is very easy to be integrated with the strategic mine planning, no? So when I say strategic mine planning, it's also called pit optimizer, stuff like Whittle, MPV scheduler, Deswik. I mean, those are type of software that do the economic optimization. Instead, slope optimizer, what it does is a optimization of the slope. And then we want to integrate. Next, please. Okay, so this is just to say that, so the output from the design of a slope typically go into the economic optimization. Next, please. Okay, next. Let's skip this. Next. Okay, then if, these are the last 3 slides. So now I relate it to another work package. So we've seen, hopefully, for work package 1, what it means topological optimization. No? And there are a lot of aspects that still are not there. No? So I would like to come up with a vast general methodology and software to do topological optimization in all the context. A point still of work is, okay, but what happens if you have a lot of joints, no? So here is to show you a methodology where all these joints, you see this is a bedding, and cross joints. So when you have such type of joints, the strength is anisotropic. Anisotropic means that depending on the loading direction, the strength is different, no? And this is to show you this. So here you have a rock sample. If you load like this along the vertical direction, this is a strength, no? If you instead do a 50, around 50, 52, no? So you simply take the sample, but now you rotate the sample. So now the direction of loading comes at an angle of 52 to the direction of the joints. Well, the strength is less than half. So this is just experimental data, not to say that when you have joints, the strength of the rock depends on the position of the joints with respect to the load, the direction of the load. Next, please. And this is like a work I've done in collaboration with this consultancy. So they're based in Tucson, Arizona, called St. Nicholas. And what they do, so this is their model, which I find it very, very good. So what they do is like for all the joint sets, so for those of you who works on the joint sets, hopefully this will ring to, all the joint sets are featured by deep direction, deep, mean length, mean spacing. So you put all the data of the joints. Then you have the data also for the strength of the intact rock, and you work out this. So this will be cohesion and internal friction angle as a function of the dip in the slope. Next, please. So now, this was a case study where we wanted to apply our software to this very highly jointed rock mass, and the dip now with the inclination of the bedding. So we did a different, where in each case we have a different inclination of the bedding, no? And if you change the inclination of the bedding, it will change the response of the slope, how the slope behaves. Next, please. So now, for it, the idea is we have now a function which expresses the anisotropy, the anisotropic strength of the rock. So now, when I look at a single failure mechanism, I need to discretize. Because if I'm here along this direction like this, it means the rock will have a certain strength. But if I'm like along this direction, we'll have a different strength, no? So along any failure mechanism, there will be a different, I discretize, and then for each of these direction of loading, I will pick out the corresponding strength, because the strength is anisotropic, no? But doing this now, I can account fully for the effects of the joints on the rock mass strength, and therefore, next please, and therefore to do topological optimization also in this context. So here what we have is, you see, for every slope, 1, 2, 3, so we have different cases in terms of this function, cohesion and friction angle. They correspond to a different bedding dip, and also here a cross-section azimuth. So basically the idea is, you have this rock with all these joints, no? All these joints. And then you say, okay, if I do a vertical cut with a certain azimuth, you will cut the joints in a certain way that gives you a certain function. If now, rather than this cut, I do a cut with a different azimuth, I will cut the same rock mass, but with a different inclination of the vertical plane, and therefore will be different, the type of anisotropy. The beauty of this model, it accounts for this. So basically this means we can use this to design wherever are in the mine with respect to the joints, to the discontinuities. And here again, here is a traditional slope, straight slope, and the corresponding optimal slope, where the safety is similar. So here the brief was 1.3 factor of safety. Again, the optimal slope always managed to be steeper than if you look at this overall slope angle, no? The overall slope angle goes from the toe to the crest. The optimal slope always managed to be steeper than the planar counterpart. Next, please. So this is really the sort of result. So in a way, to measure, you do overall slope angle of the optimal slope minus the overall slope angle of planar slope, and you see the increase in inclination. There is here an interesting case where we cannot do better. And this makes sense, because this means that the joints, daylight on the slope. So clearly, if you have joints such that the behavior is fully, completely structurally controlled, maybe we cannot do better than the planar slope. But there is always a gain in terms of the steepness. Next, please. Thank you for your attention. I reckon that this has been perhaps a bit, well, too much detail, but feel free to ask any question on anything, not just on the technical side of the presentation, but also on the exchanges. Any question is welcome.
Thank you, Professor Stefano. I saw that you have done the work with anisotropic rocks, but in 2 dimensions. Yeah. I think the next step that we will part of in is anisotropic rocks in 3 dimensions. Is that
I love to hear that, yes. No, absolutely. If you already work in this area, absolutely. It would be very, very nice.
very interesting your work here in Colombia. We have a prospect, a gold mine in La Colosa mine in Ibagué. There I was participate as geotechnical engineer, and we didn't take into account this geometrical optimization, of course, because we worked there in 2011. So your work is new and is very interesting because improves the overall slope angle with the same factor of safety. In Chile also, we have open pits in Caracoles mine that we didn't work with optimization. So here in South America, we can use this research very good, very well.
I couldn't have a I would say, better question than this. No, really, yeah, I feel excited, especially, as you mentioned, if there are like a case studies, data that we can work on, that would be brilliant. So absolutely. I'm really excited to hear this. We should definitely follow up after here.
Okay, Professor. Thank you.
Anyone else from where?
Thank you, Professor Stefano. Thank you for your presentation. I comprehend your research like reduce the rock waste, the waste of rock in the excavation, yeah? But I don't know the assumption of the layer of the strata where is the mineral. For example, the gold, because if you begin to excavate at the beginning, if you encounter gold, you don't optimize if you need all the area to extract the gold in this strata. What is the assumption of the deep of the strata where is your mineral? Depend on your results of this deep of the strata?
Yes, perfect. Let me tell you. Can we go back, Andy? Sorry, I need to go back to, so you keep going until I stop you, right? Go, keep going, back, one back, stop there. Okay, so basically, thank you for the question, first of all. But what I want to say is this. The mineral, clearly, absolutely crucial, and where the mineral is where you use a block model, no? And typically you use a piece of software, Uitili. You know Uitili, right? So Uitili, but what Uitili does, Uitili or any other pit optimization software, they will tell you this is the optimal pit shell where to excavate on the basis of the mineral, not where the mineral is, by economic optimization, no? Because as we know, if you are below cutoff point, you don't want to excavate the mineral below cutoff. Uitili and all this program, the slope is there as a constraint, okay? So, if I tell you, look, this slope is 45-degree inclined, Uitili will generate an optimal pit shell where the slope is 45-degree, okay? Now, if you use instead this, what slope optimizer does is to say, okay, but I want a different shape of slope. I don't know yet where the slope is, because Uitili tell me exactly where to put the slope, right? But the idea here is, instead of going 45, use this different shape so that is 50 degree, okay? Now, then Whittle works the same way. What Whittle does is, for this, Whittle tells you, here should be the slope rather than it should be here. So Whittle, on the basis of where the mineral is and the slopes, he says, okay, this should be the excavation, no? And also Whittle tells you the depth, no? Because I've used Whittle myself, so I know that the depth is something that comes up out of the optimization. No? There are different pictures, and then you say, okay, where do you want to put the pushback? No? But the picture, including the depth, right, comes out of Whittle as an output, okay? But typically in Whittle, you will give a constant angle. Or maybe you do a constant angle for first layer, constant angle for second layer. So here the idea is, I do the slope optimization independent of Whittle, because when I do slope optimization, it's based on the geomechanics, no? On the rock's strength parameter, da, da, da. And I come up now with an angle that varies with depth. So the bench, no, the bench is always the same, but this angle is not, the angle may vary with the depth, such that you have, say, 50 as overall slope angle. This is the input for Whittle, is the slope I give to Whittle, and Whittle, in the same way, will come up with a picture that gives you the highest MPV for the given block model and geotechnical constraint, where the geotechnical constraint is the angle that defines the slope. It makes sense? Yeah. So in a way, I don't worry in the sense that I can tell you that the exact location, no, the picture is always the pit optimizer that does it. But here is, because as input we give better slope, then there will be less waste rock. Because if the overall inclination is higher, that is what allows as an end result to get less waste rock. Cool. Yeah. Anyone else? Don't feel shy. I can see some. Or it's good to see some young faces at this type of event.
I want to say something, but in Spanish, okay? Pues yo no sé si todos disfrutaron de la misma forma que yo la presentación, pero es maravilloso ver cómo se combina la ingeniería, las ciencias de la tierra, los modelos matemáticos, los modelos computacionales, y se puede hacer algo bellísimo por hacer un ejercicio de la minería de una manera más responsable. A ver, trato de explicar un poco de qué se trata el proyecto. Me lo explicaron incluso hace poco, yo no soy ingeniera de minas. Fíjense en algo muy importante, la minería es fuertemente criticada en el mundo entero, como algo que debemos abandonar, ¿cierto? Como si fuera lo peor de lo peor, y necesitamos de ella para todo lo que hacemos en nuestro planeta. Y la Unión Europea le dio 1 millón de euros a esta investigación. ¿Por qué? Porque estamos mirando cómo hacer un ejercicio más responsable y más sostenible la cadena de suministro de minerales críticos para la transición energética. Porque son necesarios. No estamos pensando simplemente en la minería de oro o de carbón, estamos pensando en cómo hacer una extracción responsable de los minerales que son críticos. Y este trabajo lo vamos a hacer en Colombia, este modelo lo vamos a evaluar en Colombia para una mina muy importante para nosotros aquí en Colombia, que es Cerro Matoso. Me explicaban que las minas de cielo abierto tienen un impacto ambiental bastante fuerte. Y el ángulo con el que se hace la extracción, dependiendo del ángulo que se escoja, el impacto es más alto o menos alto. ¿Y de qué depende? Estudié muy bien con qué ángulo hacer. Entonces me decían, vea, si el precio de metal está bajito, entonces no se piensa mucho en el impacto ambiental y se hace de tal manera que el impacto es… Si el precio del metal está alto, entonces se busca un ángulo con menor impacto. Y este modelo lo que busca es encontrar el ángulo óptimo para que haya balance y una mejor escogencia de un ángulo que permita hacer una extracción sin un impacto fuerte, sin un impacto tan negativo. Ojo, el impacto nunca es cero. Siempre hay un costo, siempre hay un riesgo. Disfruté mucho tu presentación, Stefano. Es hermosa. Estamos en búsqueda de encontrar una mejor manera de hacerlo. Pero yo quiero decir algo aquí muy importante, que es lo que Stefano no les dijo en la presentación, porque él como buen ingeniero disfruta, es esta parte, que es bellísima. Nadie aquí lo puede negar. Pero Stefano es un CEO impresionante. Él logró una alianza, y ustedes lo vieron en la presentación, de 10 universidades del mundo. Él trabaja en la Universidad de Newcastle y consiguió alianza con varias universidades europeas, con universidades en Estados Unidos, en Australia, en Asia y en Colombia. Y en Sudamérica, la única universidad que hace parte de esa alianza, la única facultad que está en ese gran consorcio que se ha ganado este Marie Curie, es la Facultad de Minas de la Universidad Nacional de Colombia. Y es algo por lo que tenemos que estar realmente felices, realmente entusiasmados, y vamos a poner en este trabajo lo que nos destaca: trabajo y rectitud. Lo vamos a hacer con entusiasmo, con compromiso, porque es nuestro deber, como la Facultad de Minas de la Universidad Nacional de Colombia, pensar en estos problemas, aportar soluciones que hagan que la cadena de suministro de materiales críticos que son esenciales para pensarnos en un presente y en un futuro, se hagan de la mejor manera. Eso quería decir en este espacio. Y de verdad, mi más sincera admiración, Stefano, por todo tu conocimiento científico, técnico, que es fabuloso y es único, pero también mi más sincera admiración por tu estrategia. Lograste reunir al mundo, a 10 universidades del mundo, a pensar en este problema. Y estamos aquí en la Universidad Nacional de Colombia y en nuestra amada Facultad de Minas, muy orgullosos y muy contentos de pertenecer a esta alianza internacional, porque esto es una alianza mundial, global, y pertenecemos a esa alianza para pensar en problemas que son realmente importantes. Cuando se trata de pensar en transición energética, es muy fácil pararse en la orilla de criticar y decir es que no se puede hacer nada. Dejen ya de hacer minería. No, eso es lo que hacemos. Miren este hermoso lugar y miren ahí el fresco hacia en honor a las minas. Nuestra vocación es minera. Debemos irlo haciendo, el mundo lo necesita, pero hay que hacerlo bien. Y hoy Colombia está representada en esta alianza mundial. Colombia hace parte de una investigación que le importa al mundo, y quien representa a Colombia y Sudamérica en esta investigación que es de interés mundial es la Facultad de Minas de la Universidad Nacional de Colombia. Gracias.
Gracias, Decana, and thank you, Stefano, for the introduction to the overall work for the next 4 years. Basically, the Dean spoke about the importance of the consortium and how the consortium was put together. And I think that is crucial for us right now in this moment of the strategic planning that we're developing for the next 5 years, all the way to 2030, in continue strengthening these alliances. And we look forward to developing the work package number 6, which is dissemination and communication with you. And we're also very proud to be working along with the work package number 7, which is the management part. So, of course, with Professor Luger, for example, and the way his team and his students are going to contribute to the research, we hope that the international events that we will be hosting, hopefully by 2026, 2027 mostly, we're going to create a culture of international research networks like the ones we have developed. So basically, the Dean's message is that one, that we're very proud that right now we have been able to, as at the School of Mines, Facultad de Minas, be the representative in the consortium for South America and obviously of Colombia. And she stresses the importance of continue developing alliances with all those universities and the opportunity that new projects are going to come along from this alliance. So let's get to work, and thank you for your visit. And obviously it is an honor to have you this week. And it's also an honor for us to be in charge of the work package that we're going to be developing. So thank you very much, and let's get to work.